In this video, we're going to talk about level curves and surfaces. So let's just start by defining what a level curve and a level surface is. So a level curve, just really an equation involving x and y. So any kind of expression involving x and y equal to a constant. That's a level curve. And a level surface, any function of x, y, and z equal to a constant. So what's important is that you've got a constant on the right side. Now we want to talk about some geometry and how that relates to the gradient vector. So the idea is that if you have a level curve, let's say someone gives you an equation like f of xy equal constant, a really nice property of the gradient is that the gradient of f is going to be perpendicular to that curve. So let's just draw a picture. So we would be in the xy plane, we'd have some curve representing this equation, f of xy equal constant, and at any point on this curve, if you calculate the gradient vector, guaranteed it's going to be perpendicular to your curve. So when we say perpendicular to the curve, we technically mean perpendicular to the tangent vector at that point on the curve. So gradient vector gives you the perpendicular direction. There's a similar kind of fact for level surfaces. So if someone gives you an equation like f of xyz equals constant, then when you calculate the gradient vector, that's going to be perpendicular to your surface at whatever point you're interested in. So let's draw a picture here. Let's say we're in space. We've got some sort of surface. Okay, maybe just for the sake of discussion, let's say our surface looks like that. And if we identify any point that we're interested in on this surface, let's say right there, the gradient vector is going to be perpendicular to our surface at that point. And when we say perpendicular to the surface, formally what we mean is imagine drawing the tangent plane to the surface at that point. We're really saying the gradient vector would be perpendicular to that tangent plane. So gradient vector perpendicular to our surface. So let's try an example here involving level surfaces, and we'll see how the gradient vector can be useful to us. So we're going to let C be the intersection of these two equations. Now these two equations that we're seeing in the problem here, these represent surfaces in space. So this C that we're getting is actually a curve. When you intersect two surfaces in space, you're going to get a curve. So we've got some curve C that's being described geometrically, and we want to find the tangent vector to that curve C at a specific point. Okay, let's draw just a very rough picture to visualize this. So the first surface here is a paraboloid, z equal x squared plus y squared. So it's just a bowl that's opening upwards like that. Second surface is a sphere, radius root 30. So just for the sake of a picture, I'm just going to draw our sphere looking something like that. And when we intersect those two surfaces, we're going to get some kind of curve that looks like that. So in fact, in this example, it will turn out to be a circle, but we don't really need to know that to solve the problem. So that blue curve there is C, and no matter how complicated the equation for your surfaces are, even if they were a lot more complicated than what we've got in this example, we can still follow through with the method we're going to do in this problem to find the tangent vector. So what's important is that we have level curves or level surfaces in this context. So what that means is that you want to have a constant on the right side of each equation. So we would actually need to take this first equation, rewrite it as x squared plus y squared minus z equals 0. Okay, and then we could call this expression here, let's say little f. Now we've got little f equal a constant, so that's a level surface. This one here is good to go. We'll just call this stuff on the left side here, g, then we've got g equal constant. So again, that's a level surface. All right, so the idea of what we're going to do here, I think we'll zoom in on our curve C and make a plan. The idea is that C belongs to both surfaces. It lies on both the paraboloid and the sphere. The gradient of f is going to be perpendicular to our curve C at whatever point we're interested in. Let's just say this is the point 1, 2, -1, -2, 5 right there. Let's just say that's our point of interest. So the gradient of f is going to be perpendicular to our curve C because C lies on the paraboloid, and the gradient of f is going to be perpendicular to the paraboloid. Now at the same time, the curve C lies on the sphere. So it's also true that the gradient of G is perpendicular to our curve C because the gradient of G is perpendicular to points on the sphere, and C lies on that sphere. See, we're in three-dimensional space, so we can have two different directions that are simultaneously perpendicular to our curve. So that's perpendicular to our curve, and that's perpendicular to our curve. And when we say perpendicular to our curve, we really mean perpendicular to the tangent vector. All right, so I'm going to draw a third picture and we'll see how this is all going to work together. So here's our curve C. Here's our point that we're interested in. And let's say that this is our tangent vector. So I'm not going to name it. I'll just call it tangent vector for now. So the way we're going to figure out the tangent vector then is we're going to say, well, we know two directions that are perpendicular to that tangent vector. So if we just take the cross product of those two directions, gradient of f crossed with gradient of g, that will give us a direction that is perpendicular to both gradient of f and gradient of g. In other words, that'll be our tangent vector. So just draw that all together in one sketch. So let's say gradient of f is here, gradient of g is there. If we cross these two vectors together, let's label them, we'll have a direction that's perpendicular to gradient of f, perpendicular to gradient of g, and the only direction that is possible there is the direction of that tangent vector. So let's start off with gradient of f. Looking up at the top of the screen here, f is x squared plus y squared minus z, so the gradient is 2x, 2y minus 1. And then we're going to evaluate that at the point that we're interested in, the 1, -2, 5. So we can write gradient of f at 1, -2, 5, and just sub in our values, 2, -4, -1. Okay, and then we'll do the same thing for the gradient of g. So I'll do that part over on the right side of the screen. So g was x squared plus y squared plus z squared, taking the gradient, 2x, 2y, 2z. And again, we're going to evaluate that at the point that we're interested in, the 1, -2, 5. So that's going to give us 2, -4, 10. All right, so in order to get our tangent vector, all we need to do now is take a cross product and we'll be done. So I'll do the work over on the side here. I'm going to write out the first vector, which is the gradient of f. I'm going to write out the second vector, which is the gradient of g. And to do the cross product, I'm just going to recopy the first two columns here. First column, just a placeholder, and then we're going to take these little 2x2 determinants to create the three components of the cross product. So what's coming up here is our answer. We're getting the tangent vector. The way we're getting that, gradient of f crossed with gradient of g, and here's our answer coming up. Okay, so first 2x2 determinant, -40, minus another 4 is -44. -2 minus 20 is -22. And then the last 2x2 determinant is 0. So our tangent vector, -44 minus 22, 0. That gives us a sense of the direction in which that curve C is moving. And you can feel free to scale that because we're just talking about the direction of the tangent vector. So if you felt like dividing that through by -22 and you said 2, 1, 0, or any other multiple of that, that would be fine as well. So that's one way in which gradients can be useful to us, really helpful in giving the direction that's perpendicular to a level curve or surface. Thanks for watching.